Good morning. So we'll start with lecture number 10 today. Before that, just some logistics about exam number 1. So Wednesday is going to be exam number 1. It's 75 points. There'll be about 10 questions. The breakdown I've given here. So there'll be about 5 MCQs, 1 match the following, 1 true or false, and 3 fill in multiple blanks. It'll be administered through Canvas, and you'll also have to give your answers through Canvas as well. You will have the option of uploading any worksheet that you may have, but that is completely optional. So the exam is designed in such a way that there are a lot of sub-problems, sub-questions throughout. So I believe that the most amount of points that a single question has is around 3, which means that, for instance, this one fill in the multiple blanks, for instance, has about, where's that? Yes, this one here has about 12 different questions, each of which is there for about, let's say, 2 points at most. So essentially that means that the entire problem, a bigger problem, has been broken down into a series of smaller sub-problems where the steps themselves are within the problem statements. So essentially that means that you don't have to present your work, that you don't have to upload any kind of a worksheet that you would have used or anything like that, but you will have the option. Today morning I uploaded this kind of the instructions for quiz number 1 on Piazza. Couple of important things here. One is that this point here is very important. There are 2 questions that currently require this kind of a graph with seeing the color, essentially, just to differentiate between a few things. So if you're colorblind, please let me know. I think that is very important. Before Wednesday, I will try to make sure that the portion is like, instead of having just colors, maybe the graph has X's and O's or those kind of things, where it's not just color that is a differential between stuff that we would be interested in. Regarding the exam itself, it's going to be about 75 minutes. So for in-person students, the exam's going to open at 9 a.m. on Wednesday. Again, it's online, so you don't have to be here. You can take it from anywhere as long as you have a stable internet connection. So in the 2-hour window, you can choose any 75 minutes. But the exam's going to end at 11 a.m., which means that if you want to have access to the entire 75 minutes, you would have to start the exam before 9:45 a.m. On Wednesday. For distance learning students, the exam is going to be open until Sunday evening, until 8 p.m. It's going to open on the same time, which is Wednesday at 9 a.m., but it's going to be open until Sunday 8 p.m. But you'll still have the same 75-minute window, so you would have to complete it within that 75-minute window in one of the longer duration things until like Sunday evening. That's the only difference between the 2 things. For in-person students, I think it's very important that your distance learning students are also going to be on the same Piazza network. So make sure that you're not discussing any answers on Piazza until at least Sunday evening. We'll probably next Monday we'll go through a few solutions for the exam. It's not going to be very hard. Most of it is conceptual. And one other thing that I will emphasize on is the geometric aspect of it. Which is that whenever we think of these kind of W transpose X plus B, there's always a geometric interpretation for that. There's a line segment. Okay, so for what value of W, what a line segment is going to look like, another value of W, what line segment is going to look like, what exactly is bias. If you can map this all out in a geometric space, I think you'll be good. That a large portion of the quiz is going to depend on the graphing or the geometric aspect of it. There's not going to be any coding questions directly. In other words, you don't have to open Colab in order to find any kind of solutions, but you're more than welcome to. The exam itself is open notes, MATLAB, Python, Colab, anything is permitted. So you can go through and find your homework codes and use that again here as well. But again, it's not required. Most of the questions are analytical, and if not, just a simple calculator will also do. In fact, I believe that only in one question you would require this kind of a calculator. And all the other questions you can eyeball the answers, the numerical part of it as well. Is there anything else? So we covered this. So don't post solutions again on Piazza, but if you have any questions where you would have to discuss a part of the answers, please do that privately on Piazza, just to the instructors, so we'll have access to it. What else? The last one, yes. So within the quiz itself, the last question is designed in a way where you'll be able to upload your worksheet. As I mentioned before, worksheet is not required. You can choose what, if you do want to upload, you can go ahead, especially if it comes to like something like during regrade requests. Maybe that is something that would be pertinent at that time, but again, it's not mandatory at all. But if you want to do so, it's still within that 75-minute period itself. You won't get more time for uploading. Since it's part of the question, what your browser might do is it might tell you that if you're not uploading anything, your browser might say that one question is unanswered, which is fine. If you see the quiz, when you see the quiz, you'll see that the upload part has like 0 points. So even if you don't upload anything, you're still going to get the highest possible points there is. And only one PDF is allowed on Canvas, so that means that you should be able to merge this kind of, let's say you have something on Colab that you want to show us, as well as something that you have written. So that'll be two separate things, right? One of which might be just a photograph or a scan, and the other one is a PDF. You should merge it and send it rather than two separate PDFs. I believe that Canvas only accepts one PDF at a time during the quizzes. Any questions about the logistics itself? All right. So last week we ended at performance metrics for regression models. So there's one thing we had not covered, which was about model validation, that we are going to cover today, and then move on to the next topic within the course, which is going to be about clustering algorithms. There's one thing that I'm not really sure was, I'm not sure how well I explained the idea of sparsity and lasso regularization. Based on the questions I was receiving, I felt like the idea was a bit lost. So if there are, let's say, 10 features in a parameter, so in my parameter, basically theta is, let's say, it goes from theta 1 to theta 10, which means that there might be 10 features in the parameter space. The idea of L1 regularization is not to take the 10 features and bring it down to just 3 features. You're not zeroing out the parameters to make sure that just the 3 features are available. It's just that the way the 10 features are going to be designed, whenever any kind of an X projects onto the theta, only a sparse set of features are going to be activated. That is the definition of sparsity. And I tried to explain it in terms of visual features, but I don't think it was very apparent without showing the slides. So this particular slide is hopefully a better representation. So let's say I'm taking one test sample, let's say X, which is somewhere here at this spot. I can take this, a very complicated image within, let's say, any natural image sequence. In this case, it's just a landscape. I'll be able to represent that in only a sparse and limited set of parameters. That is, I can take this test sample and 0.8, which is going to be theta 1, and this is going to be like theta, I don't know, 25, and this is going to be theta 32. So just based on these 3 parameters, I will be able to represent back my X, which is where I was projecting. That essentially is what sparsity implies, which is that whenever I'm projecting some kind of a data point onto my sparse parameters, only a few of these parameters are going to be activated. Everything else is going to be 0. Only a few of them will have some kind of an activation. In this case, it's a 0.8, 0.3, 0.5, while everything else is 0. So this part won't be activated. It's 0. This is 0. This is 0, and so on. There's only 3 things within my parameter space which will be activated. That is essentially what sparsity means, and what the L1 regularization helps us achieve. So again, this is more from a, we'll in fact come back to this slide later down the course when we talk about something called autoencoders in neural networks. This is actually a slide that I've taken from there. But hopefully it is making the point of what lasso regularization and L1 regularization actually does. All right, with that, let's move on to the model validation aspect. A part of this is something that you have already seen in classification, and something that you are currently coding for homework number 3, which is about the difference between the train test validation and the usage of the validation data set, as well as the split that we try to do in order to get our solutions. Again, the goal in cross-validation is that we don't have access to, let's say we only have access to a small set of data points in our training set. Our model will vary based on the amount of training data we have. So the best way to account for it is having multiple training algorithms on small sets of data points and then looking at what the output is going to be. So if you have, let's say, 10 times, if you do this same procedure, then once your result would be probably be very high, and that is one thing that you might choose instead of just being happy with just one training algorithm. Again, it's something that you're currently working on in homework number 3. I believe it's question number 1. This is a strategy that you will use, and this is something we had seen before as well. Same thing with learning curves. This is also something that you are doing in the first question in homework number 3. Ideally, you should have this kind of learning curves. I think it's 1H, I believe, in your homeworks, but you should see something like this. With increase in training set size, your learning curve, your error also kind of increases. Now, when we saw this from classification setting, it's not very apparent why this is the case, but hopefully it is more apparent when we come to regression, because as your training set size increases, your error that you have against your learned model, because there's more number of data points, you have a higher amount of error. And this essentially is what this learning curve is telling you, which is with an increase in your training set size, your error also increases. This on the y-axis is absolute error rather than like mean error. Same thing with the sorry, I was talking about training set. No, this is incorrect. This is testing set, and the left one is training set. So in the testing set, which would be validation test set in this case, your results are going to keep on decreasing. So this is something that you'll notice in the question 1 in 1H, and these are the kind of graphs that you should be able to see when you follow this procedure for cross-validation. This is an example of linear regression versus polynomial regression. We'll discuss the goal of model validation that we'll be discussing today is talking about these kind of differences in these curves and how we can say one is better than the other. Very simply put, at least this is what you're expected to do in your homework. Very simply put, all you would do is just look at the mean square error and say that model A is better than model B, because the mean square error in linear regression is around 1.75 versus here this is around just below 1 essentially. So you can say that based on my performance metric, which is a mean square error, I can claim that 10th degree polynomial is better than linear regression. Again, it's very important to not just look at the training set, but you would have to look at validation set after every epoch in order to say that one is better than the other, or so on. So we have two very important points here, which is the idea of what underfitting and overfitting is. And the next few slides are going to discuss the definitions of this. So I'll hold off on just talking about the two points here. So cross-validation is something that we saw. Let's directly go into model complexity, which will be about the underfitting and overfitting aspect. So let's say I have this kind of data points. So I have these kind of data points, all of which are generated by this kind of a parabolic curve. So all your blue points here are your data points, and I'm trying to put linear regression on top of it. And as you can see, it's not possible, right? Because the underlying data generation process is a polynomial. It's an nth degree polynomial. In this case, it's just a second degree polynomial. But if I try to put something like linear regression, the best I can achieve is this kind of a line here, this line segment, which does not fit the data itself. So then I would have to then move on to something like a polynomial regression. Again, when I'm trying to do regression, I don't know what the underlying data generation process is. So the first thing I'll start off with is a second degree polynomial, which is this kind of a parabolic line. Maybe at this point I'll get greedy and I'll think that, okay, this, there is a certain amount of error which is not 0 at this point. Is there something better that I can do? So I'll go to a 3rd degree polynomial. I can go to a 4th degree polynomial. I can go to something like a 300 degree polynomial, right? So the question is, what is a good polynomial? What is a good degree of polynomial that I can use in this case in order to fit my data generation process? And the idea for that, or the way we would validate that, is something called model complexity. And the outputs would be underfitting or overfitting. So in this case, you have a line segment, which is a line. Your model complexity, or the amount of parameters you're using to create your regression model, is not sufficient enough. So this is something that we are going to call underfitting. And there is a point where the number of parameters that you have used in terms of your degree of polynomial is going to be more than required. And that is going to be overfitting. So you can see at this point that, and by the way, this is what we are going to call complexity. Underfitting and overfitting are both going to be complexity. You can see here that what has happened, at least with overfitting, is that there's almost this kind of a memorization that has happened. So your model knows that at all these points data exists. It knows nothing in the vicinity of those points, but it just knows that at that point my model data exists. So what would happen is, if a new data point is generated and you would have to fit it to this graph or to this curve, it has to directly fit on top of an already present data point. Otherwise the model does not know. It knows nothing about what is in the vicinity of that, right? So it knows, it cannot fit a new data point given this kind of an overfit model. The exact opposite happens in your underfitting, which is you have not given sufficient amount of parameters in order to create your model. So that means that the error is going to be very high. You're never going to get a good regression model if you don't have a good set of parameters that have already been chosen. So this, we can actually get this via plotting it and doing it multiple times. But a better way to do something like this is by looking at model complexity versus the model prediction error. So this is something that we had seen in our learning curve aspect as well before, which is that once your training data, your training error decreases to this point for a given amount of data, there will be a certain point where your prediction error for new data starts increasing. In other words, what has happened is that it's at this point you have this kind of a graph, which is your model has not fit properly yet. There is going to be a point where the best graph possible is going to be halfway stage between it's doing well on training data and it is going to be doing well on our validation data. That means that the error in both these cases are going to be low. The error for your test data is going to plateau, and this is something that we want to see, that we want you to see in 1H. And after that, after a certain point in time, your test data, the error increases. This part you won't be able to see in the homework because the complexity of the data set is not very high. So there's other kind of data sets where you'll be able to notice this, but not in the homework data set that you're using. But essentially what happens is that the validation set, the error for your validation set increases, which implies that your model is now overfitting to the data that you have. So you have to stop training at this point. We have talked about epochs, and the number of epochs is till this point has been arbitrary. We are just saying, okay, just do it for 100 epochs, just doing it for 50 epochs or 150 epochs and so on, right? But if you want an actual answer for how many epochs you need in your machine learning model, it is based on this idea of underfitting and overfitting, where you don't want to be underfitting so much where both your training and validation errors are decreasing. You don't want to be in a stage in your learning curves where only your training error is decreasing but your validation error is increasing. That would be overfitting. You want that sweet spot in the middle where it's neither underfitting and overfitting. So any in this region, any in this particular region would be fine when your validation set validation error is not increasing. That is the ideal time for stopping your any kind of a gradient descent or optimization algorithm that you might choose to get your model performance. Any question on the idea of underfitting versus overfitting? All right. So so what I just said was more qualitative. You would have to plot these learning curves and you would have to see what the results look like and then decide that this is the point where I want to stop my, my analysis or my training procedure. There's a more mathematical analysis for this, and that is something called the bias variance trade-off. To understand bias variance trade-off, we have to go back to cross-validation as an example. Let's say I have a data set of 1 million images to start with, but I don't have the bandwidth, the GPU necessary to train everything. So what I do is I need to choose 10,000 images to train my algorithm, right? But as we already know, the way I choose my 10,000 algorithm is going to influence the validity of my model itself. It might be good, it might be bad based on the training data, the 10,000 images I have chosen. That's when we do this kind of a cross-validation, where we decide, okay, I'm going to randomly choose 10,000 images, and then I'm going to repeat this. I'm going to train my algorithm, see my test results, and I'm going to repeat this 10 different times. So I'm going to have 10 different algorithms or models that are trained on 10,000 images to get a certain output. So that means that you have access to 10 different models right now. And the output of those models are all going to be different. So let's say in this case, there is this kind of a data point output that we might assume, let's say. And what happens there is that there's going to be two factors that you'll be looking at. When you do cross-validation in homework one, in the first question, you're just being asked to find the mean of all your outputs. That is more than sufficient. That is what we're going to be calling bias. But there is another quantity as well that we need to look at when you have these 10 different models, and that is called variance, right? So that, let me go to this slide here. This probably is a good way of trying to understand or motivating what bias and variance is going to be. So in this case, you have 10 different models that have been trained, and your goal is to have the least amount of error across the different models. So in a single model, you want to make sure that your output is as close to the ground truth as possible. And across the 10 models, you want to make sure the same thing is true again. This is where the idea of bias variance trade-off comes into picture. This is the ideal case. All your 10 models, in this case I don't think it's 10, it's probably around 20, but the top left case, your bias and variance is going to be very low, and this is probably the best model, the most well-trained model that exists. If you have a model that is either underfit or overfit, you'll have something like this, which is that when you train 10 different models, you won't get the same error. Think of this midpoint here as 0 MSE, which is as close to the target as possible. So when you train different models, in this case around 20 different models, there's going to be a few models which will have a error of 0, but there's going to be like 8 or 18 other models whose MSE is going to be, I don't know, this is going to be 5, this is going to be 7, this is going to be 8, and so on. In fact, let me just put it as -8. So we are looking at it in a different graph here. So essentially, that means that if you have, in cross-validation, if you have taken 20 different models and you're looking at the outputs, there's only going to be 2 outputs which are going to have 0 error, and you're going to have 18 other models which will have a different error, which is not 0, which might be very high. The opposite might happen when you have a high bias and low variance, where maybe all your algorithms have an MSE error of let's say 6, and it varies between 6.5 to 5.5. Essentially, what is happening here is that your model, your predictions are far away from what your target is, but all of them are being to the same spot. So that means either there's something like a local minima that your algorithm is always descending to when you're using gradient descent algorithm. So there's a problem with the amount of data as well. Now, the worst case scenario is the last one, which is the predictions far away from target and they vary wildly. In which case, I mean, the way we have generated this, of course, is the same thing with 0 mean. We have generated with a different mean with a high amount of variance. So whenever you're doing cross-validation, the cross-validation, you have to be wary of both these things, which is the bias and variance. So when you have taken 10 different models, you need to take the average of your MSE just to be sure where your MSE is, and then you need to look at the variance as well. Maybe one of your model is performing very well, and you're just showing us that model, saying that, oh, my MSE is this, but that's not how we always show cross-validation results. We show two things. We show the bias as well as the variance within that framework. Is this clear in terms of the motivation for what bias and variance is? So there's a different way of thinking about it. So this was more from a motivational aspect based on how you'll be solving your homework. But there's also a mathematical way of thinking about it that we'll look at now. So let's start with the data generation process itself that is random. Again, we talked about 1 million images, right? And from that, we are choosing 10,000 images. Same case, let's say we have 1 million data points out of which we are choosing an n number of data points. Here, these data points are all different. As you can see, I don't know if you can see very well, but the configuration of all these data points is different. Just look at this region, just look at this region. So all of them are coming from the same distribution in general. We have a parabolic line, we have a parabolic segment, and from that we have added a certain amount of noise and generating all these data points. If I choose some kind of an algorithm, let's say a regression algorithm that is going to model all these things. Let's say I'm choosing a linear regression. We know that this is underfitting. So what is happening that even with different configurations of data, your model is exactly the same. So this is equal to this, is equal to this, is equal to this, right? This is an idea of underfitting, where even though my data is changing, my model does not change at all. So the MSE for this, and let's say this started off with MSE is equal to 10. It is also going to be equal to the same thing in this case as well. Because again, the data is generated randomly, so that MSE is not going to change. So the randomness of that makes sure that the mean square error is going to remain the same. So what is happening in this case is that your outputs, your regression model that you have trained is going to be the same throughout. Which means that your network has now underfitted. Your model is now underfitting to the data generation process itself. The opposite of that is this kind of a thing, where again, the data generation process is different. Hopefully you can see this and this. I don't know how visible that is, but the data generation process is the same parabolic function. We have added different noise. So you'll have these two configurations of data. And when I train a polynomial regression algorithm like this, all my regression algorithms are going to be different, right? Compare this against the linear algorithm that was there before. All of the linear algorithms were the same versus all the polynomial algorithms are different. So in this case, what has happened is that there is a high variance occurs when you have chosen this kind of a regression polynomial algorithm. Yes?
When you say that the linear algorithms are the same, what do you mean by that? Because the lines have different slopes.
Oh, so I'm sorry. When I said I meant the MSE is going to be the same. So whenever I'm talking about regression, it's usually the projection of certain points on my algorithm itself, which means that the MSE in this case is always going to be the same.
You're talking about the MSE
In this case, MSE is almost going to be 0. It's going to be as close to 0 as possible in this case. So in a way, yes, MSE is going to be the same, which is 0, but it's going to be very different from in this case, where it's going to be a certain number that is involved. So what happens is that when you draw these curves, we can divide this error. When we first looked at learning curves in this case, it was almost always just a single curve that existed from 0 until a certain point where the validation error was constant at this stage, and then afterwards it kind of moved away, it kind of moved up, right? We can take this curve and we can create, we can decompose this curve into two things, which is the bias and the variance. And the bias variance is the ones that we just discussed, which is variance occurs when a model is too flexible that it overfits to the specific data. That means that the model itself changes too much across our different implementations, while the model doesn't change as much across different implementations in this, the first case, while it's opposite in the other one. So they are on different spectrums of this learning curve here, which is the bias versus the error. So the idea here is that we are just looking at the validation accuracy here. or maybe I should say the validation error. This validation error is a combination of two things, the bias error and the variance error. So the bias starts off very high in the beginning. In other words, it's not able to really understand what the data generation process is. It's always going to be a very high bias. In this case, I just put it as 10. But then after a certain while, it's going to learn and come to the perfect stage, which is going to be somewhere in the middle over here. But if you keep training, and if you keep increasing the amount of parameters, it will increase. And what increases is not the bias, because when we talk about the bias, it's the average error, and that error is always going to be 0. We'll come to what I mean by the average error later. That's more of a mathematical formulation. But the error is going to be 0, but the variance in your model itself is going to be very high, which means that this error here, which is the variance, is going to increase. So this parabolic curve of your validation set, your validation error, is a combination of two things, bias and variance. Bias starts off very high, but becomes very low later on, while variance is the opposite. It starts off very low, but it becomes very high during the later stages of your learning. And the goal for you is to find the sweet spot where both the bias and variance are low, so that you'll be able to get the best possible model for your data. So if you look at the same thing, we started this off by talking about complexity, right, which is the model complexity. So this model complexity is in fact a trade-off between bias and variance. And hopefully looking at this graph, it should be clearer, which is the idea of underfitting and overfitting is in fact a function of bias and variance. More complexity decreases bias, which we are seeing here. If our model complexity, and by model complexity here I'm just saying it's the amount of parameters I'm using in theta. So theta parameters, let's say if I'm using n different parameters, your n keeps on increasing across the x-axis here. As and when your n increases, which is your complexity increases, your bias decreases, right? Because if I go back to the original, this diagram here, if I'm giving it higher number of parameters, in this case, your MSE will go on decreasing, but only to a certain, even when it decreases, your average error MSE is 0 in this case, your variance has now increased quite a bit. And that is the last point here, which is more complexity increases the variance across your learning algorithms. Any question in terms of what bias variance is, bias variance trade-off is? Your validation error is decomposed into these two things, and you use them in order to select the complexity of your algorithm. If you want to select, if you want a linear regression or a polynomial algorithm, in a polynomial regression, what should be the power, the degree, is essentially that will be set by using this kind of a bias variance trade-off and looking at the best possible output that you can get over there. So for a linear model, your bias is very high depending on the data, at least for these 3 data points, for these 3 configurations of data. If you just put a linear algorithm, of course, it's never going to work out for you. Your bias is going to be very high, but your variance is going to be very low because when your error is always going to be high, let's say you're using a gradient descent algorithm, you're not really learning anything when your loss is always high. There's no way to update your parameters that will give you a better set of loss in this case. Low degree polynomial is exactly what you want in this case, because we see quite easily that it's a parabolic function, which is 2 degrees. So for a low degree polynomial, your bias and variance are all going to be low. For a higher degree polynomial, your bias is going to be very low. It's almost going to be 0. Your mean square error is almost going to be 0 in this case, while your variance is going to be extremely high. And the right one is what we call overfitting. The left one is what we call underfitting. So these are very important concepts. How you define overfitting and underfitting in terms of the bias and variance is what we usually use in order to say if a model is well trained or not well trained, or it's not trained enough. There's also a mathematical way of trying to come up with it. So till now I've just said that MSE is 0 and hence bias is 0, right? The reason for that is bias is the square difference between predicted and true target, which in this case is in fact your MSE. So if you're using a mean square error, for instance, in order to do gradient descent, what you're actually doing is decreasing the bias. You're trying to make sure that the bias is as less as possible, again, which makes sense because you want a model with the least amount of error, but you want to be sure that the variance is not going to increase when you're doing it. So we look at this other quantity, which is the expectation of f cap of x minus f cap of so this is the prediction, and this here is the expectation across all data points, so the mean of all your predictions. So in other words, if I go back to this, your mean of all your prediction is probably something like this. So you'll just be taking a subtraction against that mean of all these prediction. Essentially what you're trying to find is the variance of your error and the bias of your error. You're taking your mean square error and then creating this kind of a bias variance trade-off. Now this is easily seen, I would say, in terms of mean square error, but the same thing exists in any loss function. We've used negative log likelihood, we've used cross entropy loss. Any kind of a loss can be broken down into these things, which is the bias and the variance. Bias is just the this quantity over here, your prediction minus your error rate, while the variance is prediction minus your mean rate, sorry. Variance is you're taking an expectation across the square of the same thing. The mathematical part hopefully will be more, you'll use this in the homework essentially. So as long as the conceptual part of what bias and variance is clear, I think it's very important. Bias and variance is probably one of the most important parts of regression, because we use that throughout every other application. We use this idea of validation accuracy, the loss function, and training and validation loss in order to do classification, clustering. Any other algorithm that we are going to come across is going to be decomposed into bias and variance, and we'll see when to stop training, for instance. For a large-scale neural network, we'll be using this kind of concepts. If there's no other question in terms of the regression part, so the last slide here, in fact, there's a demo, online demo that you'll be able to use. It's very similar to what you'll be doing in your homework as well, but if you're interested in seeing for different amount of data, what the output may look like for different degrees of polynomial, you can use this link to go there to find it. The next part is going to be clustering algorithms. So we have looked at two big things till now, which is classification and regression. Clustering is the third thing. So the difference is, in lecture number 2, I believe, we started off by talking about two things, which is the difference between the types of learning. There's either supervised or unsupervised. The idea of supervised learning is that we have access to certain labels. Given data, which is X, I have some target variables. In classification, it's classes. So, or Y was always a kind of a class, a categorical label. In MNIST dataset, it was the numbers 1 to 10. In IRIS dataset, it was like these three classes, three, I believe, the three classes. And so that was for classification. In regression, Y was this continuous output variable, where it could be, it's something that is dependent on your x's. It's an independent variable which is dependent on your x's, but it's continuous. So the outputs could be, the outputs could span from any, it's not just an integer, it's not a categorical label, it's a continuous output. 0.5, 4.2, 4.84, any of these numbers are allowed within your Y framework. The goal in unsupervised learning is that you don't have access to Y's, that there is no class available to you, there is no output, there's no target, there's no independent variable that you have. The goal is to see what can you do just given these data points, and that is the main idea of clustering. Clustering is an unsupervised learning algorithm, so both regression and classification was supervised algorithm. What we'll be seeing now, which is clustering, is an unsupervised algorithm. So just look at the things on the right, for instance. It just appears very, at least this one here, both of them in fact appear as though they are from classification setting, right? Because usually when you see a group of these things, one of the algorithms that we saw in classification was something called k-nearest neighbors, and we just defined that anything that is next to each other belong to the same class. Now think of the same thing, but now it's that they don't belong to a particular class, but rather belong to a cluster. We are saying this is cluster number 1, this is cluster number 2, this here is cluster number 3. So all these data points belong to certain clusters, and they may or may not belong to the same classes. That part is very important. So so clustering is an algorithm grouping of a set of samples in such a way where samples in the same group are more similar to each other than those in the other group. The easiest way, of course, to think about it is that things in the same class are within the same cluster, but that's not true. You don't have access to the definition of a class to say that if something is similar or not similar. In k-nearest neighbors, our definition of similarity was based on if this was the same class. So I said that 5 of the data points are similar to class 1 or are nearer to class 1, while 4 of the data points are nearer to class 2. Hence, these set of points are class 1 rather than class 2. We don't have access to the idea of classes, hence we would have to define what specific feature to compare and what the proximity measure is going to be. It's not classes now, it has to be something else, and we'll discuss what those something else are going to be. The goal of clustering algorithms is actually to define those things, which is what we are going to be comparing against and how far or similar they are to each other. So let's look at this segmentation image, for instance. Here, if we look at this from a classification setting, I would say that this is elephants, for instance. I would classify the image on the left as an elephant. But a clustering algorithm, ideally you should know that there is this region that belongs to a certain object, but you don't need to know what that object is. You don't also need to know that this object and this object are not the same from a clustering algorithm's perspective. It is just looking at different objects and saying that this belongs to one cluster, this other object belongs to another cluster. Now we know that they both are elephants, but that's from a clustering algorithm's perspective, that's perfectly fine for it to not know that these two belong to the same category. Rather, what it needs to know that it belongs to the same object or it belongs to the same cluster. That's a very important distinction that separates classification from clustering. And we can do the same thing in the other cases as well. There's a leaf, there's an animal on top, and the leaves and animals, same thing exists. You don't even need to know that this cluster here and this cluster are, it's very different from this cluster over here. Even though, in fact, it might be the same, it is, from a clustering algorithm's point of view, it's very different. All it needs to know is the set of pixel has to belong to that cluster. Yes? The elephant, I think, is a good example. Both the elephants are the same class, which is the word elephant, but they are in two separate clusters right now. If I remove the thing that I've mentioned here, yeah. So if you ask a clustering algorithm, it tells you that this is cluster number 1, this is cluster number 2. While if you ask a classification algorithm, it says it belongs to class elephant, or you can call it class 8 or something, whichever class that elephant was in its training algorithm part. Any other questions? So there's different ways of thinking about clustering. From a news article perspective, again, these are all real life applications of clustering, but news articles, there would be a broader range of grouping of your articles in terms of, it could be business, local world, and so on. And within that, there could be other subcategories, your latest economy, markets, and so on. These are also clustering based on the articles, based on the content of the articles that the news site is doing. Usually when we think of clustering, we think of it from this perspective that, let's say I have a certain lexicon in my language. All of them belong to a certain group, so it can go to a bigger group, and that can go back into a bigger group, and so on. So this is probably one of the easiest thing to think of is in terms of languages. A number of languages can be clustered into a different hierarchy of languages. So this is like a top-down approach on what clustering might look like, where the bottommost part is from the individual languages versus the topmost part is Indo-European languages and so on. But there's a different way of thinking about clustering, which is this is the top down and probably more intuitive. And more non-intuitive is from the bottom up, which is basically this idea of species. Let's say, let me give you an example. When you discover a new species, the way you would do it is by looking at these kind of graphs where there is a higher hierarchy of species, and then there's a subspecies, genome, whatever the name, genus, the Latin names there are, and you'll come to a certain aspect. And this is the opposite of doing it. Before we have languages and we are creating clusters to find what the bigger cluster is, just to analyze all these languages. In the species part, it's the opposite, which is we have access to these clusters and we are seeing if a different species that we are looking at right now is either does it belong to an existing species or is it something new. So if you come across an application in machine learning, a very common one that you'll come across is something called new class discovery, which is that let's say I have a certain n number of classes, and this is true usually in natural images where you might have 50,000 different classes that you're training, and then somebody might come up with a completely new synthesized image, put it online, and you would want to classify that image as well, but it doesn't belong to the existing categorizations of images. So you would have to, your algorithm needs to tell you this is something new, that the network or the model has never seen this kind of a class before, and that is a new class classification. New class discovery, sorry. And it comes by because of this idea of clustering, and this is in the opposite direction. Instead of taking data points and creating clusters, we are looking at clusters to see if data points actually match the existing clusters that we have. So in both these cases, clustering is very important, which is creating clusters or analyzing based on clusters. There are different applications of the algorithm itself in clustering. Again, this is our first introduction into unsupervised learning algorithms. So it does, it's good to think of it from a high-level perspective before we jump down into the algorithm and the math part of what clustering is. Clustering happens via words as well. For ChatGPT, for instance, if you give it a set of sentences and ask it to cluster based on something, ChatGPT and ask it to cluster. This is an example where we are giving it about 4 different sentences and asking it to cluster. And ChatGPT essentially clusters this and this together and this and this together. You can read through what those are, but essentially one of them is a more fact-based statement, while the other ones are philosophical statements. It's able to cluster based on the words that it is looking at. It's able to cluster all these paragraphs. And if you ask it to explain why it's doing it, it will in fact say this. So both phrases are more philosophical in nature. Both phrases are factual and present information about current events. That basically means that any model should be able to do this kind of clustering. And this based on thing that I just mentioned, the based on thing is the idea of the similarity versus dissimilarity we were discussing before. If a particular species belongs to a genus and then to a bigger species, essentially that is the similarity in this case. So there has to be a measure that we need to define. It can be classes and classification, but in this case there is no classes, so we need a different measure. So let's look at what that is by a very simple example in this case. So I'll give you 15 different data points, 2 features per data point. This is a kind of table we have seen before. When I plot it, it looks something like this. My data matrix is on the x-axis on the top right over here. If the goal for you is to create a clustering algorithm, one simple cluster is this, this, and this. These are 3 different clusters that I can create. Whenever you're given a classification algorithm, there's always a y here, where you'll be asked, okay, is this a 0, is this a 1, is this a 2, or different classes and so on. Clustering, you're not given access to any classes, right? But I'm still telling you that you need to create some clusters out of it. And again, this is an example where I'll talk about why we chose these clusters, but intuitively it should be clear to you that all of them are closer together, that things in this cluster are closer to this some point that we have chosen, things in this cluster closer here, and things in this cluster are closer to this point. based on the closeness to a chosen point, we have now created these 3 different clusters within the data frame that we have. So this is where we'll start defining some very important terminologies. Let's start with the simplest one, which is features. Given this table, features is the 2 xi1 and xi2. We already have seen what features are. It's the same thing that we had seen before, same thing that exists within clustering as well. The proximity measure is something that is very new, which is how close is it to each other, the similarity or dissimilarity of my features to each other, each of the data points within the cluster is given by something that is called as proximity measure. So usually the way we define proximity measures is between 2 points. In this case, it could be between x1 and x2, x1 and x3, x1 and x4, and all these things. You can get a 15 cross 15 matrix based on the fact that I have 15 data samples. It's going to be a symmetric matrix, but still, it's a 15 cross 15 matrix that you can create these kind of proximity measures. Again, the idea of proximity measures is to create this similarity or dissimilarity between data points. Cluster, of course, is a group of similar data points. So on the right-hand side, we have access to 3 different clusters. And these are 2 things that we'll come to later down the line. We'll discuss more about what they are. But there's a difference between something called hard clustering and soft clustering, or fuzzy clustering. Hard clustering is that a single data point belongs to one cluster only. While soft clustering or fuzzy clustering is not that. A single data point can belong to multiple clusters. And if you want kind of an example, maybe this news article thing can be helpful here. So the same article that belongs to market can also maybe be in latest as well. That means that we have these multiple clusters, but the same article that is there in the markets could also be in latest. It also could be in, I don't know, local. So this, maybe the first article is something that is localized to your city. So while it is a market-based article, it's also a local article. Right? So it can have 2 different tags associated with it, which is the markets and the local as well. Hence, this is what we would call soft clustering, where there's multiple number of clusters that a particular data point can belong to, which is opposite of hard clustering, where a data point can only belong to a single cluster. And in this simple example that we have chosen, it's hard clustering, where we have taken all data points to be in separate different clusters. So those are the important terminologies. We'll discuss more about the hard clustering and soft clustering over the next 3 classes. The last one will be about the soft clustering part. So with that, let's start formalizing it, a little bit of math in terms of what clustering is going to be. So the first part is going to be very similar, which is our X data set will have X1 to P features, which basically is something that we have seen. The difference, of course, is that you're not going to see a Y anywhere here, which is there's no target, there's no independent variable, there's no output, whatever you wanted to call Y based on the application that you were doing, that part is not there. We only have access to the X's here. An important part, hyperparameter, if you will, is that we have to start partitioning it into something called K clusters. So this is something that we start with. We want to choose K different clusters in order to assign different data points in. So we start off with these K clusters. We'll call it C1 to Ck. And the goal of C1 to Ck, or the idea of choosing them, is the following. So each sample should be assigned to a cluster. This statement here is union from set theory. So it goes from K equals 1 to capital K. C of K is equal to X. I think it's more instructive to see it in the opposite direction. X equals union of C, which basically means that your data set, all your X's, is a combination of a K number of clusters. So every single data point is within a particular cluster. So if you represent all your clusters, or if you take a union of all your clusters, you get your data set from before. So X equals union of K equals 1 to K, C of K. Again, C of 1 can be x1, x5, x10. C of 2 can be x2, x4, x9. And C3 could be all the remaining ones, right? So essentially, whenever we say this capital C, It's just a composition. It's just a combination of all possible data points that can exist within that cluster. And once you start taking a union across these clusters, you get back your X. So each cluster has at least one sample associated with it, which is very important. What is the point of defining a cluster if there's no data point within it, right? And the last one is that this is only for hard clustering, which is that all data points only belong to a single cluster. So the intersection between, let's say, cluster 1 and cluster 2 is going to be a null set. There won't be a single point that is going to intersect between your cluster. So these are the three conditions that we need to satisfy whenever we are doing hard clustering. These are the simplest three conditions that we would have to satisfy when we were doing hard clustering. And we did do this actually when in this kind of a very simple example as well. As you can see, all data points are accounted for. There is no data point that is outside of the three clusters in this case. So that satisfies the first condition. Second condition is that among all three clusters, there's at least a single data point, again satisfied. Last condition is that there's no overlap between clusters. There's no single data point that is present between different clusters, which is again satisfied in this case. So that's for formalizing different clusters. The reason we formalize and we need this is because we want to mathematically define something called the proximity measures in this case. We'll be discussing these 6 proximity cases, proximity measures, similarity versus dissimilarity. In fact, it'll be 5. The first one is more of a qualitative difference between what the two things mean. We'll talk about cosine similarity, Euclidean distance, Manhattan distance, Minkowski distance, and Mahalanobis distance. All these distance measures, at least in fact, we saw cosine, Euclidean, and Manhattan as loss functions within our classification setting. And hopefully that should be intuitive. Hopefully that should make sense, right? What we are trying to do here is create clusters, but in classification we were using the distance. We were trying to reduce that distance in order to say that this is based on the same class or this is a different class. So any and all proximity measures that we can use in clustering, we can go back and use that in classification as well. We can go back and use that in regression as well in order to create our algorithm, in order to create our loss functions. So let's start with the first one, which is the similarity versus the dissimilarity. Again, this slide is more of a qualitative difference. So similarity essentially means that given any 2 points xj and xk, similarity function will have a large value if the two things are very similar to each other, as the word says, which is opposite that of dissimilarity. And both of these are proximity measures. We can say that a certain function, which is a similarity function, the proximity measure for that, if it's very high, that means that they're very far apart from each other. They're dissimilar to each other. Actually, sorry, what did I say? I think it's the opposite of what I just said, which is if the similarity is very high, then that means the proximity, that means the two data points are very close together. And it's the opposite in the distance function, which is if my distance function is very high, then that means the two data points are very far away from each other. And we can define any kind of a function with on top of it, right? This is something we used in SVMs as well. Whenever we were doing radial basis functions, we define the distance between 2 points to say if something is far or if something is nearer, the kernel functions that we were using. Cosine similarity is the first similarity function, and again, we had seen this in SVM as well, whenever we did the AB cos theta part, when we were trying to find the distance, the margin. This is exactly what we had used before. So the definition between 2 points Sj and Sk is given by x transpose xk cos theta, which is, I think an easier way to say this is AB. So cosine similarity cos sim, let me say, is equal to A transpose B, which is your transpose in your inner product space, which is also given by norm A, norm B, cos theta. So all these things mean the exact same thing. Your cosine similarity between two vectors A comma B, or two features, data points A comma B, is going to be A transpose B, which is the same as norm A, norm B, cos theta. In a Euclidean space, this norm is going to be 2, but of course you can define which space you're in order to define the cosine similarity functions. So this is giving you exactly the same thing. This is the L2 norm which is norm A, this is norm B, and the top part is A transpose B. So this equation, in fact, is cos theta equals A transpose B given by norm A, norm B. So even though it might look intimidating, it's not that. It's just your norm function that you're taking. If you just think about it as A and B, it's a very simple cosine similarity, like a cos theta function that can exist. The important thing here is to see what the angle and how that angle changes with your result. So let's say we are looking at the angle between two features, xj and xk. So cos theta we already know can go from -1 to 1, right? So if I were to draw a cos function, it would be something like this. So it goes from 1 to -1 in this case. So that means that when cos theta is 1, there's a maximum similarity between A and B. When cos theta is -1, there's the least amount of similarity. That means that they are both looking in the opposite directions. While if cos theta is equal to 0, the points themselves are completely uncorrelated, is what the cosine similarity is telling you. You can use this, of course. I can use this cosine similarity within my simple example and create this kind of a 15 by 15 matrix. And between x1 and x1, the cosine similarity, of course, they both are exactly the same. So it's going to be 1. Then I can do the same thing against all different aspects, right? So you can get a 15 cross 15 matrix to find what the similarity is between all data points. And I can analyze it based on what the values are going to be of your cos theta. So again, it's just a very simple similarity measure that we can use. We can turn it into the opposite direction as well. Just by making it d equals 1 minus cos theta, we can make it into a distance function rather than a similarity function. The difference, of course, is that d now goes from 0, 2, rather than your cosine similarity going from -1 to 1. Your distance now goes from 0, 2. But again, it's the opposite here. If your distance is very high, then that means that your data points are not similar to each other, versus cosine similarity was the opposite. If it was 1, that means data points are very similar to each other. This slide we give an example and tell essentially where we would want to use cosine similarity. So it's effective to evaluate, and especially for sparse vectors with many 0 entries. So when you are, let's say, in your homework or in your exam, you're given this kind of vectors and asked to find the proximity measure between vectors. When you see that there's a lot more zeros within your vectors, then cosine similarity is something that you should use to find the proximity measure. The reason for that is beyond the scope for this class. We won't go into details for why the sparsity is helping. But essentially, if you look at examples, you'll be able to see why as well. So in this case, we are using just x1 transpose x2, which is the same thing that we were using before. And then norm x1, norm x2, you'll find a cosine similarity between this x1 and x2. Think about why by thinking about what the cosine similarity would be from a element-wise perspective. If you were doing it element-wise rather than vector-wise, that will help you with the derivation. But again, the reason for that is not something that we're going to be covering within the course itself. Any questions on cosine similarity? Probably the most straightforward similarity measure that can exist. It's just measuring the angle between two vectors. That's all it's doing, that's it. So again, this is another example for the same thing. You're just measuring what the angle is, and we can get this kind of a 4 cross 4 matrix. Same thing, before we had a 5 cross, like a 15 cross 15. In this case, we have 4 points, x1, x2, x3, and x4. We can use those in order to create our cosine similarity measure. Based on it, we can now decide, okay, which are the clusters, right? In this case, if you look at x1 with x1, it is 1. It is the maximum, of course. It's the most similar with itself. Now you'll find the ones that are even more, so 0.98 and 0.92. So these two are very high, right? That means that x4 with x2 and x4 with x3 is very high, which essentially, ideally, that means that you want this to be in a single cluster. compared to this, which will be in its own different cluster. This is what cosine similarity will give you in terms of how I can do it. Actually, one second. So x1, x2 are least similar with orthogonal direction, and x3, x4 are most similar with smallest angle. So the angle between them, of course, is given by this. Now, you can have complications to this. This is a very simple 2 clustering, but if I give 3 clustering, this is where things might get even more, a bit more complicated. If I were to ask you to create 3 clusters based on this table, this is just for 2 clusters. This seems pretty straightforward, but when you have to do this for 3 clusters, you would have to look at the numbers carefully to decide where the clusters are, where they need to be, right? So in this case, maybe this would be a good clustering algorithm, because x2, x3, sorry, I think. So x2, x3 should be one cluster, this. So if we had 3 clusters, if we had asked you to give, if this was examined, we had said, okay, give me 3 clusters based on this data point, this is how you would have to differentiate them and get results. The next measure is a distance measure. Again, probably the simplest one, which is Euclidean distance, L2 distance. This is something we have seen, and probably the most easiest distance that can exist. Given 2 data points, it's the Pythagorean distance between the 2 things. So you just take this, and find the square of the 2 and take the square root to get the distance here. As simple can be. In terms of distance measures, it can go from 0 to infinity. 0 is maximum similarity, and infinity is minimum similarity, or in other words, it's the opposite thing from a distance perspective. Maximum distance is infinity versus minimum distance would be 0. This is, of course, the most used distance measure. This is absolutely true on data points that exist in the normal space. So whenever we give you features like x1, x2, x3 in a 3-dimensional space, Euclidean distance should be your choice in terms of using the, any kind of a distance measure. But as soon as we say that the data generation process is going to be different, or it's a higher dimensional representation space where it's not 3-dimensional anymore, but it's like 10,000 dimensions, Euclidean distance fails generally. And you can think of why from a more qualitative analysis of distance, right? So from here, if I tell you the distance from here to something like Atlantic Station is about a mile, usually when I say that, it's like I'm looking at an L2 distance, which is if a bird flies from here to there, they have to cover about a mile or something like that. But in reality, if we want to walk over there, it's going to be very different. You have to adhere to the streets, there are streets, and there's like a hilly region somewhere near Home Park, which means that you'll be covering more distance than 1 mile. Right? So in a higher dimensional representation space, we don't know how that topology is going to look like. So in that case, L2 distance generally fails. We cannot use it in those scenarios. Even in this 2-dimension, as I said, in Atlantic Station, it might or might not work all the time. But generally, it's a good approximation, L2 distance. But in a high dimensional space, you have to avoid L2 distance as much as possible. There are better distances for that. Again, the simplest distance, L2 distance, given x1, x2, x3, x4, you can calculate the distances, and based on this matrix, you'll be given this matrix. This is probably one of the most common exam 2 questions that you'll find. Given this kind of a matrix, the question would be, how would you make clusters around them? And it's just based on the distance. All you're going to do is find the least amount of distance and say that these 2 must be in a cluster versus these 3 must be in a cluster, and so on. So another distance measure, not Euclidean distance, is Manhattan distance. Manhattan distance is based on the fact that you can only go in coordinate distance directions. So Euclidean distance was between like something like this, which was like this. This would be the Euclidean distance. But Manhattan distance is, this is, let's say, 3 units. This is 4 units. So 3 plus 4 would be 7 units for Manhattan distance. For something like Euclidean distance, this would be 5 units. And again, a qualitative way, and one of the reasons it's called Manhattan is because of, in New York City, you have all these grid-like structures. So if you want to go from one place to the other, you have to walk across these this grid streets. right? So that means that you can't just cut across buildings here. You have to go across a street, and then you have to take a right and go to the street again. So go along the street again. So this is a Manhattan distance where, and qualitatively, this is given by L1 norm, or the L1 distance. So whenever you were using that kind of a norm, I believe in homework number 1, you were in fact finding the distance, a Manhattan distance or a Euclidean distance of the difference between data points. So we usually use this whenever we have this kind of a categorical labels. So in classification, sometimes we might use this because you cannot go from class 1 to class, there's nothing called class 0.5. It is either class 1 or it is class 0. So these are categorical labels. And that is where we might use something like Manhattan distance to differentiate between labels, let's say. So similarly, as I showed before, the distance between x1 and x1 is 0. But then the difference between x1 and x2 would be something like this, 2 plus 2. That would give you 4. So you would have to walk across a certain 2 units and 2 units down to give 4, and so on. So Manhattan distance is based on the L1 norm of distances. Of course, you can generalize these two things, your L2 norm and L1 norm, in order to get something called Minkowski distance. So Minkowski distance is essentially d of xj xk. In previous cases, Euclidean distance r was equal to 2. So whole square, square root, right? 1 by root 2, 1 by 2, which would be square root of this statement here. That would be L2 norm, or your Euclidean distance. L1 norm is the exact when r equals 1, which is norm 1, and the whole thing is just 1 by 1. If we take the same thing, and we can now extend r to infinity, or the opposite to 0 as well. So you can have r to be any number between 0 to infinity, and it's going to give you all different distances. So that idea itself, that concept, is what is called as Minkowski distance. And there are 2 named distances within this, which is important for us. One is when r equals infinity, and the other one is r equals 0. The properties of this, again, are beyond the scope of this course, but what they represent is important for us, which is when r equals to infinity, the maximum element in the difference vector is taken, while when r equals 0, the number of non-zero elements in the vectors are taken. So I think this is better if I show it in terms of the outputs here. So in this particular graph, this is the same graph from before. So if I look at the this one, the L1, the pairwise Manhattan distance, let's look at from between x1 to x3. So Manhattan distance, I move 3 units. Now you move 1 unit down. So 3 plus 1 is 4, right? And the same thing, if I look at Euclidean distance, I move here, which is 3 square plus 1 square root of, which I think comes to about 2.8 over here. Which would be my answer. If I want an L infinity norm, which is the maximum of my feature distances. So the distance here is 3, this is 1, the maximum of those two will be 3. So the L infinity norm is going to give me 3 distance between x1 and x3. The pairwise L0 norm, L0 norm, is the number of non-zero distances, number of non-zero features. In this case, this is 3 and this is 1. Neither of these are 0. Hence, you have a 2 over, I'm sorry, I think I'm looking at the wrong thing here. X1 and X3, yes, this is correct, 2. So this was incorrect. I was looking at 4 over here, and apparently 3.162 when you take the root. But this is going to be 3, and this is going to be 2. Is this clear? All we are doing is taking the non-zero elements in my features to get this L0 norm, while L infinity norm is the maximum of the features. In this case, it was 3. So we are taking 3 here. Again, these 4 are the most important norm-based distances that we can use. That's L1 norm, L2 norm, L infinity norm, and L0 norm. All of them represent different aspects of different distances, And it'll be more clearer when we actually use this in some examples. But essentially, they give us different ways of trying to understand the pairwise distances. The last one is Mahalanobis distance, but it's very important. So we'll cover that during Monday's lecture. So that's it for today. Best of luck on your exams on Wednesday.